Hi guys, welcome to your second lesson in Unit 7. Today we are going to be talking about enthalpy. And so I say it like that because I want to emphasize the H in it, enthalpy, because its variable is an H, and that's not to be confused with something we're going to learn about later called entropy. So enthalpy is the heat content of a system when it's at constant pressure. So it describes the thermodynamics, in other words, like the heat transfer of physical and chemical processes. We cannot measure enthalpy directly, just like we can't measure heat directly, but we can we can measure enthalpy changes. And something I want to take a second to point out here is, remember way back in Unit 2, we talked about kinetics. Sometimes students get a little confused with the difference in kinetics and thermodynamics. So let's say that we are looking at a reaction. All right. So kinetics is all about this portion. What happens? How do we get from point A, or the reactants, to B? That is kinetics. So did we have a catalyst? Did that speed it up? Did we go through 2 steps, 1 step, whatever it might be? That's all the realm of kinetics. While thermodynamics is all about where we start and where we end. Okay, so thermodynamics, all that matters with enthalpy, especially what we're talking about, is how much energy we had when we started and how much energy we had when we ended. And we've seen this on a graph before. That's the change in enthalpy. So in thermo, we're worrying about where we start and where we end. It was kinetics that paid attention to how we got there. So speaking of that, enthalpy is what we call a state function. The value depends only on the state the system is in, but not how it was reached. So the example given here, we could start out at the base of Mount Kilimanjaro and we could go straight up to the summit. That'd probably be real hard. Or we can take this nice windy path up to the summit. No matter which way we go, we're at the summit. And our position and our elevation at the summit only depends on the fact that we're that high in the air. It has nothing to do with how we got there. Whereas a non-state function does depend on how we got there. So heat and work are examples of non-state functions. In our mountain climbing example, the time it took us to get there, that's 100% a non-state function, because it would absolutely matter if we took this path versus this path. So as I mentioned before, we put that delta in front of H and it becomes delta H, or the change in enthalpy. Sometimes this is also called the heat of a reaction. So it's the heat amount associated with that reaction. How much heat is absorbed when that reaction occurs, or how much heat is released when that reaction occurs. And the difference, what that ends up being then, is how much energy, so in our reactants, we have to break bonds. We'll talk more about this in our next lesson. And then in our products, we're forming new bonds. So the sum of the heat of a reaction is how much energy had to go in to break those bonds, and then how much energy is released when new bonds form. If this value is higher, we had to put more energy in. We're going to have an endothermic positive delta H. And if this is larger, if it's more energy out, then we're going to have a negative delta H, and that's exothermic. So a thermochemical equation, this really doesn't even deserve a slide to say what a thermochemical equation is. It's really just a reaction that's written with its enthalpy value. All right. Typically, they're going to be in kilojoules. I talked about before how we're dealing with large amounts of energy, and so a lot of times, or large amounts of heat, and we put it in kilojoules just so we have smaller numbers. Something that we need to know, if we have a thermochemical equation, here in a minute, we're going to talk about manipulating it. And so here are our rules. If we multiply a thermochemical equation through by a coefficient, then we multiply the energy by the same. That makes sense, right? So this thermochemical equation tells me that when 1 mole of hydrogen combines with half a mole of oxygen to form 1 mole of water, 286 kilojoules is released. So I multiply that by 2, and I have 2 hydrogens reacting with 1 oxygen to make 2 waters. We're going to have that same amount of heat times 2. We're always going to show our states of matter because the amount of energy required to break a bond in hydrogen gas could be different than the amount of heat required to break a bond in liquid hydrogen, which that's really hard to form. I don't even know if that we actually have, but you get my point. And then the other thing, if the reaction is reversed, the sign is reversed, which again also makes sense because if the forward reaction here releases 286 kilojoules, then the reverse reaction would need 286 kilojoules, or it would absorb 286 kilojoules. A lot of times in this, we're going to be seeing something delta H naught, or this little like degree symbol. That indicates a standard state. And so we're going to have like a table, or you're going to be given standard state values. And that just means that they were determined through a set of reactions or experiments that were carried out at standard states. Typically, if it's a concentration, it's 1 molar. And if it's talking about pressure, it's 1 atmosphere. So depending on the type of reaction, we can call the delta H, or the change in enthalpy, we can give it the name of a specific reaction. So for example, if we're looking at combustion reactions, so burning an oxygen gas, then we might call that the enthalpy of combustion. So it's when 1 mole burns at standard state. It's kind of like when we had K as our equilibrium constant, and then we called it Ka if it was for an acid, and Kb if it was for a base. Same thing. Enthalpy is just the change in heat of any reaction. Enthalpy of combustion is specifically a combustion reaction. And you're shown some examples there on the screen. If we are forming something, the enthalpy of formation, this is one that we do need to be hyper aware of because we're going to use these values to then calculate overall enthalpy. And so the enthalpy of formation, which is given delta H naught with the little f, meaning that that's formation, is the change of reaction in when exactly 1 mole of a pure substance is formed from free elements in their most stable states under standard conditions. So what do we mean by that? We mean the product has to be a pure substance. It can't be a mixture. So we can't form more than one thing. It has to be one pure substance. It has to be 1 mole of it. So notice here, all of my coefficients are 1. Those look like 2's, but they are meant to be 1's. And then they are formed from only elements. So nitrogen, oxygen, calcium, oxygen, carbon, bromine. They're elements in their most stable state under standard conditions. So remember, nitrogen, oxygen, bromine, those are all diatomic. So that's why they're O2, N2, and Br2. That's their standard state, right? We don't, oxygen gas, like O2, doesn't have to be formed. That's just how it exists in nature. Calcium, just solid calcium metal. Graphite is just solid carbon. That's their naturally occurring states. All right, so that's what all of that definition means, and that's what in your POGL, that's what the entire POGL was about, right? Was looking at what is a heat of formation reaction, what's not a heat of formation reaction. So if we then have an overall reaction, so reactants turning into products, it's not a heat of formation reaction, it's a whole reaction. We can then use the heats of formation to calculate the overall enthalpy change or the overall heat of reaction. And the way we do that is we're going to take the sum of the heats of formation of the products multiplied by their coefficients. Then we're going to subtract the sum of the heat of formation of the reactants. This is going to be, this equation right here is on your reference sheet. And you'll always be given those heats of formations that you need. Now, something to point out, let's say that, and you'll see this in a minute, oxygen gas is one of your reactants or products. You're not going to be given a heat of formation for oxygen gas because it doesn't have to be formed. The heat of formation is 0 because that's its standard state. Whereas if it's like carbon dioxide has to be formed. So you would be given a heat of formation. And you'll see what I mean in just a second. So let's start with a super simple example. We're given this overall equation, A plus B is in equilibrium with C. And then we are told the standard enthalpy of formations of both reactants and products. And we're asked to calculate the overall delta H of the reaction. So remember, our formula is that we take the sum of the delta H of formation, so the heat of formation of the products, and we subtract that from the sum of heat of formation of the reactants. So my product is C. Now this one's going to be real simple because all our coefficients are 1, so we don't have to multiply by a coefficient. So our product is C, so 523 kilojoules minus, now our product, or excuse me, our reactants are A, 433, plus negative 256. So then when you do that math, you get 346 kilojoules. Now, that means that this is an endothermic reaction, so it needs 346 kilojoules of heat, or it absorbs 346 kilojoules. All right, so now let's do a couple real life examples. So here is an example of a table of heats of formation. We're asked to find the delta H of reaction, so the heat, the enthalpy of the reaction for each of these using the table. Now, they actually give you oxygen and graphite, but in a problem on a test or quiz or whatever, these might not be given to you because they are 0. You don't have to form oxygen gas. You don't have to form solid carbon. It's in its natural elemental standard state. That's how it occurs in nature. So those could even not be given to you. All right, so our product is CO2, so negative 393.5. Now we would subtract our reactants, but in this case, it's just 0, 0 plus 0. So for this whole reaction, the formation of carbon dioxide, it releases 393.5 kilojoules of heat. All right, this one, we're going to start with our product, which is nitrogen dioxide. So see my coefficient here of 2. So I'm going to multiply by 2 because we're making 2 of them, not just 1. Then I subtract. Now I'm going to do all of my reactants. Again, I have a 2. So I got to multiply by 2. And then oxygen gas is just 0. When you do this math, you should get negative 114.1 kilojoules. Nothing too crazy. We're just doing all of the products minus all of the reactants. You've got to make sure you use your coefficients. Things in their standard state are 0. So now, what if we have a reaction that's actually a combination of other reactions? We can use something called Hess's law to then combine those reactions and combine their enthalpy values to get the overall enthalpy change for the overall reaction. So Hess's law states if a process can be written as the sum of several stepwise processes, the enthalpy change of the total process equals the sum of the enthalpy change of the various steps. All right, so here's an example, and I am going to fix, there's a typo right here, so this should say carbon dioxide. Okay, so our reaction is carbon and oxygen gas forming carbon dioxide, but it actually happens in 2 steps. The first one, carbon combines with half a mole of oxygen gas to make carbon monoxide. Then that carbon monoxide combines with another half a mole of oxygen gas to make carbon dioxide. Each of these individual steps have their own enthalpy of reaction. So when we put these two steps together, we can cross out terms that are on each side. So this is just like crossing out your intermediates or your catalysts back in reaction mechanisms. I'm left with down here in the sum, they just dropped everything down and then they crossed it out, but same idea. And then we combine like terms, and so we get carbon plus oxygen gas makes carbon dioxide. So then what we see is that we just add, since these two reactions add up to the overall reaction, we just take negative 111 plus negative 283, and we get negative 394. So the total enthalpy is the sum of the steps. So something to remember, we talked about this in a previous slide. If we multiply through by a factor, then we have to multiply the enthalpy. So this one is from here to here is times 2. And then if we reverse it, we just reverse the sign. So if you'd like, maybe pause this and try it on your own and then resume. So we are trying to determine the enthalpy of formation of iron 3 chloride. So what we can do is combine these two, cross out the like terms. Now, something I should have pointed out before, because we're using standard enthalpies of formation, sometimes you do end up with fractions as your coefficients, and that's okay. Just treat them as the number that they are. So 1 plus 1/2 gives me 3/2. Chlorine gas creates iron 3 chloride. So now because I added these up, I didn't have to manipulate them. I didn't multiply through, I didn't reverse. I'm simply going to add up my enthalpies, and I get negative 399.5. Easy peasy. All right, so here's my overall reaction. Here's my two steps. Now I have nitrogen, nitrogen matches. I have 2 oxygens. I have 1.5 down here. I have 2 nitrogen dioxides, but only have 1 down here. So clearly we've got to multiply this by 2, which means we have to multiply the delta H by 2, which makes it negative 114.12. Now my 2 nitrogen monoxides cancel out, and then I can add everything else into plus 2 O2s, because remember, I multiplied this by 2, so this becomes 1. Then I have 2 NO2s. So when I add 180.5 plus negative 114.12, I get 66.38 kilojoules. All right, last example. So we are told, and we're kind of combining everything now, when a 2-gram sample of pure phenol is completely burned according to the equation above, 64.98 kilojoules of heat is released. So in other words, our delta H of this whole reaction is negative 64.98 kilojoules. So it says, use the information in the table below to answer the following. First, count the molar heat of combustion of phenol. So here, this is how much was released when 2 grams. If I want the molar heat of combustion, just like these are, I need it in kilojoules per mole. Well, I know how many grams were burned, so I'm going to convert that into moles. 1 mole of phenol is 94 grams. So that gives me 0.0213 moles. Well, we know that that many moles released 64.98 kilojoules of heat. So I'm going to divide, and that gives me negative 3050.7 kilojoules per mole. So that is the heat of combustion of the molar heat of combustion of phenol. So now it says to calculate the standard heat of formation in kilojoules per mole. Well, this is using our enthalpy formula, but now this time we have the whole kilojoules per mole equals, now I'm going to do my products, 6 times negative 393.5 plus 3 times negative 285.85 minus my reactants. I don't know delta H of formation for phenol, but then it would be added to oxygen, which is just 0 because it's in its standard state. So I end up with negative 3050.7 equals negative 3218.6 minus, and when I solve, I get negative 167.9. So that one wasn't a Hess's law. That was an example of like a free response question where we used the enthalpy of formation equation. All right, so look at that, y'all. I'm just at 22 minutes. Go me. I will see you guys next time.